So in this lecture, we're going to describe the strain tensor. But before we do that, we have to describe something called the displacement vector. So the displacement vector is usually given in a symbol u, and it has components u, v, and w for the x, y, and z components. And all the displacement vector is a vector that points from where a point is in the material originally to where it ends up in the final configuration. So let's do an example using one of our rubber bars. So here's our experiment. We have our rubber bar, and here's a sketch of the original configuration, so nice and straight. So let's just mark a few points for us to track. So we'll pick one here kind of in the middle, one here, one kind of off to the side, one here. So we'll track 5 points, something like that. And what I'm going to do is try to line these up approximately in our sketch, just as best I can. Okay, there we go. So here's our original configuration. So now let's deform it and draw a sketch. And I'm going to do it quite extreme, just to exaggerate the effect. So there we go, the original configuration and the deformed configuration in blue. So what's the displacement vector? Well, the displacement vector is actually a field. So it's actually defined for every material point. So if you imagine covering this bar in an infinite number of points, and at each point in space, there's a vector that points. And so you could imagine filling this as an entire field of points where there's a mapping that goes from a point where it is here to where it is here. So for the corner, you can kind of see how that goes. And so the displacement vector is a function in our two-dimensional problem here of x and y. So every point in the original configuration, it just simply points to where that material point moves to in the deformed configuration. So this is going to be an important concept for us to compute the strain. So to compute strain, we're going to have to think locally. So what we're going to do is we're going to imagine 3 points really, really close to each other somewhere on the bar. And that's going to allow us to evaluate the strain is right here locally at this point. But what we're eventually going to want to do is calculate the strain kind of uniformly as a function of both the y direction and the x direction. But let's just focus on our 3 points for now. So here we've zoomed in on our 3 points in an xy coordinate system. I'm going to call this point O for the origin, this point A, and this point B. Then we're going to apply some load, and there's going to be some deformation, and so O is going to move here, and we'll call its new place O prime. B is going to move here, we'll call that B prime, and A is going to move here, we'll call that A prime. And of course I'm just exaggerating things here because ultimately what we're going to want to do is to consider small motions. So each of these 3 points is going to have a vector. And that vector is the displacement vector. It points from the original place the point is to where it ends up in the final state. And so here, our displacement vector is evaluated at point 0, 0. Here, the displacement vector is not quite the same because you see that this vector is bigger than that one. And so we need to evaluate the vector at this x location. And now what we're going to do is we're going to assume that points O and B originally are a distance dx apart. And now what you can imagine is in a little bit what we're going to do is assume that dx is small, so we're going to have to limit as those 2 points approach each other. In this direction we're going to assume that it's dy apart. Okay, so what that means then is this vector here is not evaluated at 0, 0. It's evaluated at the point dx, comma 0, and this one's evaluated at point 0, comma dy. And now if there's no deformation, there can still be a displacement field. So if I take my little triangle here and you imagine that I could mark point B and point A in the original configuration, I could have some motion that moves point O there, but then this vector would end up being the same. It would just be kind of slid over. This vector would be the same. So I can have a displacement that is not associated with deformation. But you can see here there's significant deformation because these points no longer line up. So if u is not constant in space, if the displacement field is not constant in space, there's going to be strain. So now we can see the obvious strain in this field, because if I measure this line here, in the original configuration it's 5 centimeters. In the final configuration it's 6.5. And we can clearly see that we started with an initial right triangle here. And we can see that we started with an initial right angle here, but now it's squinched in quite a bit. So the displacement field is intimately connected to the strain, and all we have to do is use geometry to relate the displacement field to the strain field. So let's consider a simple deformation. So let's consider that point O moves here, and let's assume that point B moves here. And let's assume that point A moves there. So our displacement vectors in this point are going to look like this. So there's one pointing here, one pointing here, and one pointing here. And so there's no motion in the vertical directions, but we can see there's elongation, because as we move from this state to this state, something has stretched out. So how do we understand the strain of the line element OB? So this would be what we would call the strain in the x direction. So let's remember that originally these line elements are separated dx apart. So to compute the strain, we have the length of line O prime B prime minus the length of OB divided by the length of OB. So let's start with the line element O prime B prime. So point O prime moves by a distance given by its displacement field, right? So we have our displacement vector at this point is given as that, u and v. And so by the motion we see, there's no v component, so that's just going to be 0, so there's only u. At this point, there's the component u, but it's evaluated at the point dx, comma 0. And so the value of u at this point is just given at the origin. Here it's a little bit further from it. So how do we compute the value of a function when it's kind of close to another one? Well, we use the Taylor series. So it's u at 0 plus the partial derivative of u with respect to x, evaluated at x equals 0, times dx. So the total distance from O prime to B prime is given by dx, the initial length, plus partial u with respect to x, evaluated at the origin, times dx. So that's the new distance for that line. Now the distance OB, the original distance, is just minus dx, and we just divide by dx. So that tells us that the strain in the x direction is given by the x derivative of the x component of the displacement field. So now let's consider the analogous vertical motion, where now we have these points all just sort of move upwards. So this has the vertical component of the displacement vector v, evaluated at 0, 0. This displacement vector is given by, the motion here is given by v, evaluated at 0, comma dy, where the dy, if we remember, is the distance between points O and A in the original configuration. So now what we want to do is we want to evaluate the strain in this direction. So the strain in EY is just given as the distance from point O prime to A prime minus OA over OA. So by analogy, I think you can see that the distance from O prime to A prime is given as dy, the initial distance, plus the partial derivative v with respect to y times vy. Because again, if v does not depend upon y, so if the value of the vertical component of the displacement field is the same here and here, the points just shift up. and there would be no strain. So there's only strain if these 2 points have a different vertical component of the displacement field so that they can drift apart from each other. So now to compute the strain, let's just go ahead and fill everything else in, which is nothing more than the original distance O to A is just given as dy. So you can see all the dy's cancel, and the strain in the y direction is given as that. So now let's consider a deformation. And just for simplicity, let's say the origin doesn't move, but point B moves to here, and point A moves to there. I'm going to call that angle alpha and that angle beta. Okay, so how do we figure out the angles alpha and beta? So to find this distance, all we have to do is know how far this point is moved out and the original distance of this line, right? And then we can say that the tangent of alpha is equal to this distance divided by this distance. So what's this distance here? Well, we have to go back to the displacement vector. So this displacement vector is u evaluated at 0 and dy. And so we know that that's just u evaluated at 0, 0, plus partial u with respect to y times dy. But in this example, just for simplicity, u at 0 is 0, so there's no component there. So that distance there is nothing more than partial u with respect to y dy divided by dy. So the dy's cancel, so we just have the tangent of alpha is equal to partial u with respect to y. Now we're going to use our linear approximation that says that the tangent of alpha is equal to alpha when alpha is small. So that means that our angle alpha is just partial u with respect to y. Finding the angle here is very similar. So again, we're going to have our displacement vector here, which is only going to have a vertical component v. And this point is evaluated at dx, 0. So that's v at 0, 0 plus partial v with respect to x dx. And so we're going to do the same thing again. So we're going to say that the tangent of beta is that distance divided by that distance. And again, since in this example, just for simplicity, we took v at the origin to be 0, we have partial v with respect to x times dx divided by dx. So the dx's cancel, and again, making an approximation for small angles, our angle beta is equal to partial v with respect to x. So how are the angles alpha and beta related to the shear strain, or the angle the shear strain or the shear angle when this thing deforms? Well, we can see that it has to depend upon both alpha and beta, because if alpha and beta were the same but alpha was that way, that could just denote a rotation, right? So if alpha were going the other way, we could rotate with no deformation. But we can see here we've clearly got a whole new angle here, so these points have come inwards. So what before we called the shear strain, which we gave this symbol gamma, in this case would just equal alpha plus beta, because it's the change in angle of these two line segments right here. So it's just the sum of those two things. So it's equal to partial u with respect to y plus partial v with respect to x. So here's our results. Now I have to admit I was being a little bit careless in this video because I was doing some sort of simplifications. You might notice that the motions and the geometry that I did could be coupled. So if all these points move simultaneously, there's a lot of coupling between both the elongation and the change of angles. However, in the notes that I have, we've done that a little bit more carefully, and we'll see that these approximations here are always good, and the limit a very small deformation. In the limit of large deformation, the game gets much more complicated, but we're always interested in the case of small deformation. So how can we understand this? The partial derivative of u with respect to x. Now remember, our displacement vector in 2 dimensions is going to have 2 components. So the x component and the y component describing where all these points move. So let's think about what it means to have a derivative of the x component of the displacement vector in the x direction. Well, so here's points O and B. If u is constant everywhere in space and there's no variation in the x direction, then these points can just move together, so there's no strain. So the distance between the points stay the same. If point O moves a little, but B moves a lot, then there's elongation. Or there could be compression, O could move this way, whatever. But if these 2 points, if there's a gradient in the x component of the displacement field, those points are going to change in their distance apart. Likewise, for here, everything is exactly the same. The strain in the axial direction is given by the derivative of the vertical component of the displacement field with respect to the y direction. Shear strain we can understand with our Lego model again. So if there is a derivative in the x direction of the vertical component of the displacement field, meaning that as I move in x, the amount these points move is not the same, right, then there's shear, right? So these could move up, but if B moves up higher than O, that means there's a derivative in this direction of this displacement. And then likewise for this one here, right? So if U, the horizontal displacement, changes with Y, then it means A slides over more than O, and so there's a tilting of the lines. And the 2 have to add because there could also be just a rotation. So a rotation this way means that the amount that one changes is exactly canceled by the amount that one changes. So those 2 would subtract, but when they add, we have strain. So now we're in a position to find something called the strain tensor. So we're going to use the symbol E. I'm going to put 2 lines under it because it's a tensor. So in 2 dimensions, the on-diagonal components are just the partial of u with respect to x and the partial of v with respect to y. So those would be the strains in this direction and this direction, so what we might define as normal strains. The off-diagonal components are going to be the shear strains. I'm going to introduce this funny factor of 1/2 that will become apparent why that's there in just a minute. So we're just working in 2 dimensions now, so this is a 2x2 matrix. In 3 dimensions it would be 3x3. So we'll write the full thing out in a little bit. And again, the on-diagonal components are elongation of elements. So this is this component, this component, and the off-diagonal components are how much the thing is shearing. And so this is called the strain tensor because if we go back and we look at our definitions, these are just the different components of strain. So the axial strain and the shear strain. Now the only thing that's a little weird here is this factor of 1/2. And the only reason the 1/2 is in here is to relate it more readily to the displacement field. So some of you might be familiar with this notation which denotes the gradient. So the gradient is a vector operator, and when we take a gradient of a scalar field, we get a vector field back. If you're not familiar with the gradient, then you might just have to skip this section and it might not make a ton of sense. But the gradient of the displacement field, so the gradient of a vector, is defined as a tensor, which has the following form. So you can see the gradient of a vector in 2 dimensions, it's a 2x2 matrix. In 3 dimensions, it's 3x3. But it's also all the cross derivatives. So the x component of the vector is derivative of the x, y, and z direction if we had a third component. The y component of the vector, the derivative of the x, y, z component. And so the reason that we have this factor of 1/2 is it's convenient to relate the strain tensor to the gradient of the displacement field. So you can see that this has kind of the right components, but it's not the right mix of these. So another definition is the transpose of a matrix, which simply swaps the rows and columns. We use the gradient of the displacement vector, and we think about its gradient and the transpose of its gradient, then we have a fairly simple relationship to relate our strain tensor to the displacement field. Which, using our gradient notation, ends up being this simplified form right here, where the strain tensor is just related to the gradient of the displacement field plus the gradient of the displacement field's transpose. So this is going to be a key relationship for our formulation of linear elasticity.